Hey all, Exidian here. In part 2 of my 6 crop AFK automatic harvesting and cooking farm, wow that's a mouthful, in part 2 of that I covered what a moving item filter is. It's a design of item filter that I made, and how it works and what it's used for. But I did not cover a tutorial on how to make one. So I figure I'll do that here. Just a very quick recap. This is a standard item filter. You have an input chest, a bunch of chests with items that you want to sort things into. So like if I put seeds in this input chest, they'd end up here, for example. Or if I put walls in this input chest, or one of these types of walls, they'd end up in this chest, etc. And then you have an overflow chest where things that aren't sorted, or things that aren't in any of these chests end up going. Standard item sorter, item filter, it's called sometimes. But if you want to do automation with these items without moving them manually yourself out of the chest, you run into a problem. See, if I put a robot arm here to, say, for example, grab dirt ground out of the chest, we run into the issue that it will grab the entire stack of dirt ground, leaving a hole, or an empty slot, that could in theory be filled by anything, thus breaking the item filter. So, if you want to automate with the items that you filter out, a standard item filter, item sorter design will not work. Instead, what you need is a moving item filter, or automation-friendly item filter. This is a design I made. And essentially what it does is the items that get filtered or sorted out don't end up in chests and instead end up on these conveyor belts where they're moved, where they can be used elsewhere in automation. So I've already covered how it works in part 2 of my harvesting and cooking farm, so feel free to go check that out. But let's cover how to build one. So we'll start with the filter itself. They are quite a bit bulkier than a standard item filter, but the way it works is you place down a table. Let's light this up a little bit. Okay, you place down a table, but with a 1-tile gap between the table and the chest, you place a chest below the table. You could, now that chests can be rotated and whatnot, you could actually do this facing any direction, but we'll do below just for this example. Then you place a robot arm facing upwards, facing downwards into the chest. This arm will take items from the chest and put it on the table. And then you have an arm facing upwards into the table. This will take items from the table and put it into the chest. Next, you will put an arm facing left on the left side of the chest. This is your input arm. It will put items into the chest to be filtered. Now, if it puts an item into the chest that doesn't belong, that item will drop to the ground here. So below you will place a drill facing upwards, like so. Let's actually move this torch there. When an item does enter the chest, and it belongs in that chest, it'll get picked up as a stack and placed onto the table. One item from that stack will be put on the table on display. The other items will drop to the ground here. So we need to pick them up with a drill facing left, like so. Now I'm going to repeat this design just so we can see how one filter connects to another. So table, chest, arm, 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 and then drill, drill. Now I will cover how the conveyor belts connect, but first let's do the wiring since the conveyor belts will cover that up. So you will need essentially 2 sets of wire connections. one goes along this middle row here and is made entirely of cross circuits so that it is completely separated from all of the rest of the filter, or all the rest of the filter. And then the other wire needs to power this drill, this arm, and this drill, or then this drill, this arm, and then this drill. So for that, we will place a wire here, and a wire here. So now we've connected this drill, and this arm to the wire. And then along the top, I'm going to go under the table, like so. You could go above, but you might not, your signal might not reach far enough if you do it that way. So this just saves a little bit of wire and makes it so your signal stretches a bit further. And then just keep that going along the top like so. And then we put a wire here, and a wire here, and then if we were to extend it further, we'd put another wire here, so on and so forth. So we're just going to power this on really quick, just to test it out. As you can see, we're not powering the middle drills, or the middle arms, but we're powering everything else. And then if we test this out here, we are powering the middle arms only and nothing else. So real quick, let's just set this up for success as best we can. So we're going to actually make sure these signals get extended as close to the filters as possible. So we're going to add a logic circuit pointing right into the middle wire, and then another logic circuit pointing right into the middle wire, and then we're going to actually replace this wire with a cross circuit. That way it won't get we won't get any feedback when we add in a generator here. It won't interfere with anything. But now this generator with these two logic circuits will allow this signal to be extended as far to the right as possible, so that we can extend these out as far as possible, which, by the way, is 5 is the limit for how far we can extend these outwards. With this design, there's other designs that I've come up with, like instead of 1x5, it's a 2x3, etc., etc. Anyways, so that is the filter. Now let's throw in the conveyor belts, last but not least. So the output drills, these top drills that will actually provide the output of the filter, they will have conveyor belts on their right going straight up, like so. And the wrong item drills, the ones that will get any items that don't belong in this section of the filter, we will place 2 conveyor belts pointing right below the drill, and then 2 conveyor belts pointing up to the right of that, forming this L shape. So then once again, 2 to the right, 2 up. If we were to continue this, we could keep going. That is the completed item filter. Now let's cover, these moving item filters are quite sensitive to timing, so let's cover the timing circuit itself. Now I did show in part 2 of that series that this middle line here needs to receive 2 1-tick pulses in order to prevent timing or lag from becoming an issue, and then this top line needs to receive a 1-tick, slightly less than 1-tick pulse that is on after the 2 1-tick pulses are done, and then off before the 2 1-tick pulses start again. So let's create that. So we will start by making just a basic timer. Keep in mind this is going to be a little more spread out since I'm building timer here and then these, but we'll start by creating our basic 1-second timer. So very basic, the most basic 1-second timer you can get. It looks something like this. It is on for 1 second, off for 1 second. Now this timer, let me actually turn off this for a second. This timer has a number of issues. One is if you turn it off at the wrong time, the circuit stays on forever, which with drills would cause the tables and chests to break, so we don't want that. Now that can be remedied by placing a delay circuit between the lever and the clock. This delay circuit guarantees that no matter when we turn on the lever, that doesn't fix this problem, my bad. The other problem that we have is that when we turn on the timing circuit, depending on when we turn it on, it will only be on for, say, half a second or so, because it always delay circuits always act at the same exact time, regardless of when a circuit's turned on. So if this turns on right now, it was only on for maybe 3/4 of a second, but like if I turn this on, okay, bad example. Oops. There, that was only like maybe half a second. A better example. So in order to make sure it's a full second, we can add a delay circuit between the lever and the logic circuit. This delay circuit will guarantee that no matter when we turn the lever on, this clock circuit will be powered at an exact 1 second interval. That way our first thing is on for 1 second. This helps improve the timing of the robot arms. Now, the other problem, where if you turn it off with the wrong timing, it'll stay on, this problem here. This can be remedied as well. For example, one way to remedy it is to put a logic circuit between the delay circuit that turns the clock off and the wire that connects to it. So now it's got a delay circuit between it and that logic circuit before the delay circuit, and that logic circuit is connected to your lever. This way, if your lever ever turns off suddenly, power will stop going to this delay circuit, which allows no matter what your timing is, this clock will not cause problems for you. Now, our clock is a little more complicated because we have some other circuitry involved, and this solution will not be sufficient because it can put our thing in a state where even though the clock is off, certain other circuitry stays on, and if we log off, that'll cause problems. So we actually will need to solve that a different way. But before we get into that, let's cover the one-tick pulses. So a one-tick pulse is very easy to create. You put down a logic circuit, 2 electricity sticks, and some power input. When the power input is on, it'll create a one-tick pulse. When it's off, it won't do anything. So every time it turns on, we get a little one-tick pulse. The basic reason as to why this is that when it turns on, the logic circuit is receiving power and it has electricity sticks telling it that it should move that power along. However, one tick later, it realizes that there's actually 2 electricity sticks, which in total means all 3 of its inputs are considered on, quote unquote, and so it realizes the mistake and one tick later turns off the pulse. So we're going to also create our one tick pulse. Let's just move it back a little bit. We'll put it right here. Now, we don't actually want this to be, if we just turn this on, we don't want it to be a 1-tick pulse every other second, right? Because 1 second on, 1 second off, and it only is whenever it turns on, so every 2 seconds we're getting a 1-tick pulse. What we actually want is a 1-tick pulse at the start of a second and a 1-tick pulse at the end of a second. So the way that we can do that is by adding in, if we add in another just logic gate here, we've changed nothing yet, but if we put a delay circuit aiming downwards into the top of this logic gate, we are now creating a slight delay hiccup between the logic gate turning on or the logic gate turning off and the delay circuit turning on, which allows the logic gate to be on most of the time, but every time we switch to on or off, the logic gate flickers off for a brief moment and then turns back on. This makes it so our 1-tick pulses are now happening every second. Specifically, they happen at the start of the second and then at the start of the second. Or at the start of the first second, and then at the start of the second of the 2 seconds. That's a little wordy, but I hope that made sense. Now, for the other pulse, the longer one, we need to add in a logic circuit aiming upwards, and we'll put in a generator here. So now this has become essentially a NOT gate. It will only be powered when this part of the clock is off, as you can see. And then in order to make it work better with the timing of this, of the 1-tick pulses, we actually need to rectify that timing a little bit. So we will add a logic circuit pointing rightwards, a delay circuit behind it pointing rightwards, and this will be our output. Now, to make it not interfere with the generator, we put a cross circuit down. So if we put some lights here, we can actually see that it's working as intended. So we'll connect this up. As you can see, we get the 1-tick pulse, then the 1-tick pulse, then this is on. Then when this turns off, another 1-tick pulse, another 1-tick pulse. Now this, as is, works mostly fine, but once again we have the problem that if you turn it off at the wrong time, you can get into issues. So in order to resolve that, we're actually going to keep this lever here, but we're going to add in a logic gate to turn the whole system off, but only at the correct time. So this logic gate will point down. We will have a delay circuit pointing right into the logic gate above this lever, and then we'll just run wire here, not above this delay circuit. Now, no matter when we turn this this timing circuit off, it will guarantee that there are either 2 1-tick pulses that happen or no 1-tick pulses that happen. Like so. So that is the setup, wiring and whatnot for it. Real quick, let's just throw in our items that we want. So let's do wood here. And then we will put in a bunch of filler items into this chest. This must be filler, by the way. It cannot be the item that you want to filter. That would be, that does not work. Has to be something that you don't expect to enter the system, and it must be all slots except the 1 slot, where we will then put our 1 wood. And we'll do coral here. sure would be nice if there was a way in Core Keeper to just hold down right click or something and be able to add in all of these items real quickly. Oh well. Alright, so now that's all set up. Let's add ourselves a input chest right here. And just for our own purposes, we will also have an overflow chest right here. Did we have? Yeah, we have the wire there. Okay. And then we'll put down our overflow chest. And let's turn the system on. Alright, now if I put in, let's grab coral seeds and where's root seeds? So we'll put in coral wood, coral seeds, and root seeds. We can see that the wood goes up to the top, the coral wood goes up to the top, and the seeds and root seeds go into the overflow chest. Thanks for watching. I hope this was helpful. If you have any questions, you can reach out to me on the Core Keeper Discord server. I'm under the name Exidion, EXXIDION. I check out the circuitry channel a lot, so feel free to post and share your ideas or ask questions for help, whatnot. Thanks.